I got a quick question, if that's all right.
Oh, yeah. Email, right?
Yeah,
Yeah, I haven't had a chance to, but I did see the email.
okay. Well, it's just something I could ask here, but I thought, I just, because I was trying to get a start yesterday, but
Yeah.
I'm like, oh, I could also just ask in class.
That's true. That's true.
Sorry.
Uh-huh. Let me pull it up, actually. Six.
I had to start taking the elevator. Every time I ask you a question, I take the stairs and I always sound out of breath.
Okay, so you had a question about the temperatures, right?
Yeah, because I was, for this, like I tried the different like combinations for that. I couldn't like find like line that lines. That's what my main thing is. When like how would I go about finding the reasonable reference set? Because I tried to do the film temp
Yeah,
and like try to use like the 120 and 25 and do that, and that didn't really work.
yeah.
And I also did like some of the stuff from the notes and that didn't work. So I was just trying to figure out what.
Yeah, so for this one, so the reason the 120 and 25 don't work is these are separate movements, right?
Yeah.
So the oil is coming in 120 and the water's
Yeah.
coming in 25. So for these ones, I think I may have just used 120 and 25 to compute the temperatures, because you don't know the outlet temperatures,
Yeah.
right? Reasonable reference. Oh, okay.
Because yeah, I didn't know if you.
So I think probably for this one, I mean, you can kind of assume that the temperature of the oil is going to drop.
Yeah.
But usually it's not going to drop too much. Although actually, if you look at the solutions, you can kind of see here that the temperature really doesn't drop at all.
Okay.
And so, the temperature of the oil point was down to 119. So
I
for
see.
this one, I think I just evaluated the property at the inlet temperatures.
I think I overcomplicated that because I was like looking at all that. I'm like, no, because I also tried to look at the notes.
Yeah,
And then I was just like, oh, just give them there.
yeah.
But so is there also a calculator for the oil or is that just for water?
It's only for the water. So
Okay.
the oil, I think you have to actually look in the textbook for that one, which I know actually not everyone. So let me look up what properties I use for the oil, and then I'll just send those over to you.
Okay, for sure. Thank you.
And then yeah, question prompt 3 2, right?
No, I was just wondering if the temperature was the same thing.
Okay.
Yeah, so yeah, that was just the main thing because I was trying to do the homework and like I don't want to like keep trying over and over.
Yeah,
to
yeah,
get the
that's
temperature
fair.
and get the properties.
That's
wrong,
fair.
so,
That's fair.
Yeah.
Yeah. Yeah. If it doesn't say, I would just do the
Okay.
That's always decent.
On the exam, are you just gonna give us
Yeah.
the, oh, okay.
Yeah. Mhm.
That's the only thing that's tripping me up though. Okay.
Yeah. Well, it helps my grading be a bit easier
Yeah.
too, because everyone's using the same numbers. So
And then, will before, Tuesday, will you have the homework 5 solutions posted?
yes, yeah. Homework 5 and homework 6 solutions will be up.
Alright, for sure.
Yeah, homework 5 I'll probably post tomorrow. And then homework 6 will be early, right after it's due, basically. Yeah.
Hey. Yeah, I figured out the issue I was having was what the homework, it's just because the values aren't in the calculator yet. You're gonna have to show me. So, what we call it. What the text was. Oh, I haven't even looked at it. Oh, okay. Yeah, that's what I meant. I'm like, wow. Yeah. But you have the textbook for this class? Yeah. Can you send me the table for the? No. I've seen it. I didn't play out. It's 1 o'clock. What happens when you say like you guys somewhere? What happens when you like leave on campus, you just don't think about what time is. Dr. Twitter. Dr. Trans. I don't know if I should say this, but last time we did the midterm, Flo was like, oh, this is way too easy. I want to harden. He said specifically just for him, you know, everyone else.
All right, I'll make a version T for Troy
No,
next midterm.
Oh, please.
I'm just saying, he sounded really confident.
Instead of version T for Troy, make it version T for Travis.
For both of you.
Saying, he said, I don't care if Fran knows this, so I just thought I'd let you know.
Okay.
Not holding it. What are you talking about? I don't know. Oh. That is right. Oh, really? Really? Oh, yeah, look at that. Yeah, how you can fill it a lot.
All right, it's 1 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good. End of week 12. First week back from spring break, so hopefully everyone had a good first week back. All right, so plan for today is we're gonna finish up our lecture notes on heat exchangers. So there's a lot to cover today. Hoping to get through everything. Whatever I don't get through, we'll just kind of leave it at that, because next week we do have to start radiation, and next week we're taking the midterm as well. So hopefully everyone got my email that I sent yesterday. So I posted a bunch of stuff for you guys to help prepare you for the midterm. So I posted a study guide, just like the first midterm exam. I posted a sample exam. The sample exam is just the exam I gave 2 years ago or 3 years ago when I taught this class last time. I don't have solutions for that exam, but just like the first exam, if you want to try those problems and then talk it over with me or discuss with me in office hours, I think that's probably the best way to do that. And I posted homework 6. So homework 6, it's the due date is fairly short, just because we have to get it in before the midterm. But it is shorter than the other assignments, and so just to give you guys some practice with heat exchangers and free convection, which we haven't had a chance to practice up until this point. Okay. All right. I think that's about it. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. So let's pick up where we left off on Tuesday, which was about heat exchangers. Okay. Remember, I abbreviate these sometimes as HEX, just because heat exchangers is kind of, a long thing a big word to write, or it's long to write when you're up here writing a bunch of words on an iPad. Okay, so what is a heat exchanger? So heat exchanger is a very common engineering device that's used to exchange heat between two flowing fluids. Okay. So there's lots of different types of heat exchangers, lots of different types of designs, geometries, setups. The one that we're focusing on in this class is the concentric tube heat exchanger. Okay. So for a concentric tube heat exchanger, cross section looks something like this. And so you have kind of two kind of pipes, one pipe that's kind of inside another pipe. And so inside one pipe, you have fluid 1. Right, so we'll say fluid 1 is in the inner pipe here. And then in the outer pipe, you have fluid 2. Okay. So this, this view that, I'll kind of draw a figure like this quite a lot in this unit is, kind of like a cross section of this concentric tube. Okay. If you kind of took a cross section of the concentric tube heat exchanger, kind of looking from the other way, it would look something like this, right? So inside here would be fluid 1, and in the outer annulus we have fluid 2. Okay. So we have kind of a side view and then kind of down the length view of the concentric tube heat exchanger. Okay. Okay. And so usually the case, or most, but pretty much every time you have a heat exchanger, you're gonna have one fluid that's hotter than the other fluid. Okay. And so what we talked about last time was that if you quantify this, and so for fluid 1, we'll say fluid 1 is coming in from the left, right? So say fluid 1 at the inlet and fluid 1 at the outlet. Okay. And then for the other fluid, let's say the fluids are going in the same direction. So for fluid 2, we have fluid 2 at the inlet, temperature of fluid 2 at the outlet. Okay. Remember, since these are internal flows, the temperatures of the fluid are going to change as the fluid flows along the heat exchanger. Okay. And so one way that we can quantify, or one way that we can compute the amount of heat that gets exchanged in the heat exchanger, is by simply using the inlet and outlet temperatures of the fluids. Okay. Okay. So this was kind of one of our main formulas that we talked about last time, that Q in the heat exchanger is equal to m dot, which is the mass flow rate of the fluid in one of these sections, okay, times Cp. And both of these have to be computed for the same fluid. So, don't kind of mix and match these quantities. And so, we'll say that this is, we'll say it's for fluid 1, okay, multiplied by the difference in temperature at the inlet and outlet for that same fluid. So we have T1 inlet minus T1 outlet, okay? Or if you're given the information on the second fluid, remember, these heat exchangers, we assume that they are perfectly insulated. So all the heat that leaves one fluid is going to be heat gained by the other fluid, okay? So this is equal to m dot Cp of fluid 2 multiplied by the difference in temperature for the second fluid. Question, yes?
Or is it based off of which one is a higher?
It's based on which one's the highest temperature. Yeah, so for this one, we're assuming that fluid 1 is the hot fluid, so it's going from hot to cold. And so that means fluid 2 has to go from cold to hot. Yeah.
So the heat exchanger, is that, so it's for both MCP1 and MCP2?
Yes, yeah. Yeah, because we assume that there's no heat loss to the environment. So all the heat that leaves one fluid has to be gained. Mhm. Okay. Yeah.
Obviously, we're just looking at one particular case of a heat exchanger, but is there ever a heat exchanger that exists that works with more than two fluids?
Yeah, of course. Yeah, so those would be more complex designs. So you can run, theoretically as many fluids as you want through an exchanger like this, but the analysis for that gets a lot more complicated. But
So we're not looking to those, right?
yeah,
Okay.
yeah. Because then you'd have to decide, how much of this heat's going to fluid 3, how much is going to fluid 1, how much is going to fluid 2. It becomes a lot more complicated in that case.
Are you able to computate through hand, or is it like you need a computer?
Technically, you probably could compute it by hand. You probably have to make a lot of assumptions in order to make the system kind of closed in terms of its equations. But probably, practically speaking, most people do that using computations to do that. Yeah.
Thank you.
Yeah. Question.
T2, why is it that those like and that everything's going the same direction? Why is it for the second one it's smaller?
So for that depends on the relative temperatures of the two fluids, because remember, one fluid is going to be losing heat, the other fluid is going to be gaining heat. And so with this, the way I've kind of set up this equation, with this ordering right here, we're kind of implicitly assuming that fluid 1 is hot. So it's coming in, the inlet temperature for fluid 1 is hot and the outlet temperature is cold. And if that's the case for fluid 1, that means fluid 2 must be the opposite. So fluid 2 must come in cold and then heat up from there. Exactly. Yeah. Question, yes. Okay. Yeah. Yeah. I mean, it's all, they're all going to be relative to each other, right? And so, what's hot and what's cold, one is always going to be higher than the other. Yep.
Are we also able to just always take the absolute value of that quantity?
You could. Yeah. Yeah. So I ordered this just to make sure that Q is always positive, but if you don't want to worry about it, you can just take the absolute value of the temperature difference, and then that's going to be your Q.
Thank you.
Yeah. Good questions, guys. Okay. So that's kind of where we stopped last time, or that was, I would say, one of the more important things that we discussed. The other thing that we discussed was, this idea of a parallel flow heat exchanger versus a counter flow heat exchanger. Okay. So a parallel flow heat exchanger, that's the one I've drawn up here. So for a parallel flow heat exchanger, both the inlets for both fluids are in the same location. Or another way that you can say that is that both fluids flow in the same direction. And then for counterflow heat exchangers, these are ones where the fluids flow in opposite directions. Okay. So, like we mentioned, there's lots of different types of designs for heat exchangers. And so, every different design, has a different kind of, different kind of properties. But this at least kind of gives you I would say two important categories of heat exchangers that you see out there in the wild. Okay. So I'm not going to go through all of their properties, but, I think the main thing to kind of remember is that counterflow heat exchangers, they perform better when you have a very long. And so if you have a situation where you can make a very big heat exchanger that's very long, counterflow is going to give you more performance or more effectiveness. Okay, and we'll go over that today. And just briefly, if you remember from Tuesday, for counterflow heat exchangers, one of the important hallmarks for a counterflow heat exchanger is that it's able to maintain a constant temperature difference throughout the entire length. And so that means, the longer you make it, the more performance you're going to get from that heat exchanger. Okay. Versus a parallel flow heat exchanger, this is better for when you have short lengths, just because you have a very large temperature difference right at the inlet. Okay. And so if you have to cool a fluid, or if you have to heat up a fluid in a very kind of small space, a parallel flow heat exchanger is going to perform better than a counterflow heat exchanger. Okay. But the longer you make a parallel flow heat exchanger, the less performance you're going to get.
When you say long lengths, what does that actually look at?
So length is this dimension here. Right. And it doesn't have to be a completely straight heat exchanger. So actually, we're going to do an example today where you're going to see that the length of the heat exchanger for the example is going to be like 65 meters, which you can imagine it's impossible to have a 65-meter long thing. So the way that a lot of engineering designs achieve this is by kind of coiling the pipe around. And so it's going to look something like this, right? Where each turn right here, remember, this is a concentric tube heat exchanger. So this is a tube that's going to be kind of looped around. So total amount of length in terms of the space that it takes up is not that large. But if you actually measure the distance from the inlet to the outlet, that might be something like 65 meters from there. Yeah. Mm-hmm. Okay, so that was just a summary from last time. So what we're going to talk about today is that we're going to go a bit deeper into computing heat transfer, different ways to do that, and we'll end today talking about something called the effectiveness of a heat exchanger. So how do you take a heat exchanger and quantify how effective it is at doing its job? Okay. All right. Any questions on this before we start moving on to some of the newer stuff? Okay. Okay, so let's go from here. So, we have these formulas for the heat transfer, right? So these formulas are very useful, but the weakness of these formulas is that they require us to know the outlet temperatures, well, both the inlet and outlet temperatures of the fluid in order to compute Q, okay? Okay. And sometimes you do. Sometimes you do have this information, and that's kind of the best case scenario. But you don't always have that information, right? And so sometimes you have fluid that's either coming in at an unknown temperature, but it has to leave at a known temperature, or maybe you have a fluid that's coming in at a known temperature, and you don't know what temperature it's going to be leaving the heat exchanger with. Okay. So today we're going to be talking about, first an alternative way to compute the heat transferred in a heat exchanger. Okay. So let's start with this. So let's start with let's draw our heat exchanger again. Okay. So for this discussion, it doesn't really matter too much if we have counterflow or parallel flow. And we'll kind of talk about why in a second. Okay. So we'll call this fluid 2, fluid 1, fluid 2, okay? And just like we did before, let's assume that our heat transfer is going from fluid 1 to fluid 2. So fluid 1 is the hot fluid, fluid 2 is the cool fluid. Okay, so you have Q hex going that way. Okay. So one way that we can compute Q in a situation like this is to treat it as if it were another convection problem that we've done before, right? And so we have flow, or we have heat transfer that's exiting fluid 1 via convection, and we have heat that's entering fluid 2 via convection, right? And so that's all this is. And so that's kind of why we put this in this unit too, is that a heat exchanger is essentially just an application of convection heat transfer. I did not think about that statement before I wrote it. All this is.
That's why you paused.
Yeah, I know. I was like, I regret. Should I erase or should I commit to this? I'm like, I've committed. I'm gonna write it is twice. Okay.
That's right.
I noticed when you paused, I was like, oh, I didn't put this question in there.
I didn't sleep very well last night. Okay. Convection heat transfer. So we know how to do this, right? So Q convection, we've computed this, a million times. Convection heat transfer is just H times A times the difference in temperature, right? And so I'll just say delta T in this case, okay? Right? A heat exchanger is really just a clever kind of application of this, right? And so if we can compute H, right? Then we're going to have another alternative way to compute Q heat exchanger, right? Because then that's Q to heat exchanger is the same thing as Q convection, right? Okay, so how can we compute convection coefficients in a heat exchanger? Well, we have a way to do this, and so we've kind of been talking about it for the last few weeks, right? So if we can compute the Nusselt number, the Nusselt number will give us a path to compute the convection coefficients. Okay. Now the tricky thing with heat exchangers is that we have two fluids, right? So we have kind of two areas or two domains where we have to compute the Nusselt number. Okay. So let's talk about each one individually, and let's talk about a strategy for computing the convection coefficient. Okay, so let's start with fluid 1. So fluid 1 is in the inner pipe, right? So this we know already. So for flow in an inner pipe, that's essentially the same thing as internal convection. So we did that. That was the thing we did not the week before spring break, but the week before spring break. Okay. So for the flow in the inner pipe, we have everything that we need to compute that convection coefficient. Okay. Now the tricky part, or the new thing, is for computing the convection coefficient in fluid 2. Okay. Technically, fluid 2 is an internal flow as well, but the flow geometry is a little bit different. And so for fluid 2, instead of having flow in a pipe, in a cylindrical pipe, we have flow in an annulus. And so that does change our fluid mechanics a little bit. That does change our velocity distributions, our heat, our temperature distributions. So we're going to have to change things up a little bit. So this here is new. So we need to come up with, or we need to discuss, how we're going to solve for the Nusselt correlations in this case. Okay. Okay, so for flown and annulus, just to kind of keep things simple, we're not going to get too much into the details of the fluid mechanics and the heat transfer, but there's a table that we can use to compute the Nusselt correlations. Okay, so this table is in your textbook, but it's not too big of a table, so I'll write it out here for you. So in the textbook, it's table 8.2. Or at least it was table 8.2 back in 2019. I don't know what it is now. But the way this table works is that it depends on the ratio of the inner diameter and the outer diameter of the annulus. Okay. Now, if we draw our annulus here, okay. So remember, when we say flow in an annulus, we mean flow kind of in this region in between the inner diameter and the outer diameter. And so if we say this is the inner diameter here, and we say this is the outer diameter here, okay. Inner diameter of the annulus, outer diameter, okay? If we take this ratio, di over do, okay, depending on the value of that ratio, we get the following Nusselt numbers. Okay. So this table looks like the following. So di over do, we have the value for 0, 0.05, 0.1, 0.25, 0.5, and 1.0. Okay. All right, so the Nusselt numbers in this case, so for a ratio of 0, that's basically the case where the inner diameter is non-existent, so you just have flow in a pipe. And so in that case, we don't have a Nusselt number for that because that's just flow in a pipe. We use our other correlations for that. Okay. Now, when we have this this ratio be 0.05, the Nusselt number is going to be 17.46. Okay. For a ratio of 0.1, we have 11.56. For 0.25, we have a Nusselt number of 7.37. For a ratio of 0.5, we have a Nusselt number of 5.74. Okay. And for a ratio of 1, now a ratio of 1, can't physically exist. That would mean the inner diameter is the same as the outer diameter. So this is kind of more of an extreme case. But in this case, our Nusselt number is going to be 4.86. Okay. The reason we have that last entry there is to give you a point for interpolation. So let's say that you have let's say you have a ratio di over do. So let's say it's about 0.7, right? So that's kind of in between those last two data entries. You can then interpolate in this table based on the value of that ratio. Okay. Okay, so using this table, we can compute our Nusselt numbers. Now, granted, this does have one important caveat, where this table will assume that the flow in our annulus is laminar. Yeah.
Question, so I know how you said it gives you a 0.2 interpolate between 0.5 and 1.0.
Yeah.
Does that mean all the values in the chart are linear?
You can assume it's linear.
Okay.
Yeah. It's not exactly linear, but in between the data points, you can roughly assume that it's linear.
Thank you.
Mm-hmm.
That is both flows are linear.
No, so this is just the annulus. And so even if the inner pipe can be turbulent, but that's kind of mostly separated here. So you can have a laminar flow in the annulus and a turbulent flow in the pipe, and you can still use this table.
So it's assuming like any vibrations from the center one wouldn't affect the turbulence.
Exactly. Yeah. Mm-hmm. All right, so what if you do if there's turbulent flow? So for turbulent flow, if you have turbulent flow in the annulus, remember turbulent flow for internal flows is characterized by a Reynolds number greater than 2300. So if you have turbulent flow, then you default to our general turbulent flow Nusselt correlation that we've used previously. Okay. All right, so I actually don't have the formula in front of me, the Nusselt correlation for turbulent flow in a pipe, but you know, we've used it before, right? I should just say this is for Reynolds number greater than 23. Okay. Okay, so thankfully, you know, flow in an annulus pretty straightforward, so there's not too much new we have to do with it. The only thing that really changes that if you have laminar flow, just make sure you use this table to compute Nusselt correlations. Okay. Okay, so with that, you know, and just knowing the fact that the flow in the inner pipe is just, you know, flow in a pipe, we know how to deal with it. We're able to compute convection coefficients for both the inner and outer flows in a heat exchanger. All right, any questions on this? Okay, cool. All right. Oh, actually, one last thing for flow in an annulus. Okay. So when you have flow in an annulus and you compute things like the Reynolds number, right? So Reynolds number would be the mean velocity multiplied by the diameter divided by nu, or even the Nusselt number, right? So Nusselt number is h times the diameter divided by kf, right? There's always a question for an annulus is what do you plug in for the d here, right? So for an annulus, you know, we have two diameters actually. We have the inner diameter and the outer diameter. Okay? So which one do you actually plug in for d in these numbers? Well, it turns out you do neither of them actually. So actually you plug in what's called well, technically it's called the hydraulic diameter, but it makes it sound fancier than it actually is. So what you actually plug in is we call it dH, and it's simply just the difference between dO and di. So when you're computing Reynolds number, Nusselt numbers, or if you just have any diameter that you need to compute something for flow in an annulus, just make sure you use the hydraulic diameter. Okay. Okay. If you think about it, it kind of makes sense because that's kind of the region of where the fluid is going to be in. Okay. All right. Good. So now that we know how to compute convection coefficients for both the inner pipe and the flow in the annulus, we can compute the convection resistances for each flow. Right. And if we can compute convection resistances, then we can use a thermal circuit to compute Q heat exchanger. It better be soda, by the way.
You want one?
No. I have 2 more lectures. I need to be sober today. Okay. Okay, so we have our heat exchanger here, right? I'm going to go ahead and let's assume that we have conduction resistance through the wall, right? So if you look at this wall right here, right? The wall that separates fluid 1 and fluid 2, technically this can have conduction resistance as well, right? Because as heat passes through that solid surface, that's going to provide some resistance as well, right? And so if we draw a thermal circuit here, we can say that Q heat exchanger is equal to delta T, which we'll talk about delta T in a second, divided by 1 over H1 A1 plus conduction resistance through the wall plus 1 over H2 A2. Okay. So this right here provides us another way or an alternative way to compute the Q of the heat exchanger. And notice how this does not rely on explicitly on the inlet and outlet temperatures of the fluids. Or I guess more explicitly, this doesn't depend on the mass flow rates between the fluids themselves. Okay. Okay. So that sounds great, right? So, now that we've talked about the Fullerton and annulus, we can compute this, right? Our conduction, we know how to compute that, and so that's just a natural logarithm of the, diameter ratio of the diameters divided by 2 pi KL. And then the surface area to compute as well. Yeah.
Sorry, does this matter if it's parallel or counter flow?
This does not matter if it's
Doesn't
parallel.
matter.
Yeah, so this is valid for both. Okay. Although actually where it does where the flow arrangement does matter is in the delta T, right? Now the question is, what do we use for delta T here, right? Because we actually have 4 temperatures we need to account for. So we have the inlet temperature of fluid 1, we have the outlet temperature of fluid 1, the inlet temperature of fluid 2, and the outlet temperature of fluid 2, right? So do we take the difference in temperature at the inlet, the difference in temperatures at the outlet? What if we have counterflow heat exchangers? How does that change things? Well, because the temperatures are actually changing quite a lot throughout the heat exchanger, this delta T that we compute is actually a little bit special, or more special than kind of what we've used to. Okay. And so since the fluid temperatures are changing, the delta T that we actually use here is called the log mean temperature difference. Which sounds a lot fancier than it actually is. Okay. So basically, we need to get some measure of kind of like the average temperature difference between the two fluids throughout this entire heat exchanger. Okay. That's essentially what this represents. Okay. And there's kind of a special way to kind of compute that based on kind of the knowledge that we have. Okay. Okay, so I'll just kind of give you the formula for it. Okay. So delta T log mean, okay, is equal to delta T2 minus delta T1 divided by natural logarithm of delta T2 divided by delta T1. I know I've defined none of those quantities there, but just write it down first and then we'll talk about it in a bit. Right. Okay. So this delta T1, delta T2, what do those things represent? So those delta T1, delta T2s, they represent the difference in temperatures at a physical location of the heat exchanger. Okay. So what you plug in for delta T1, delta T2, that's going to change depending on if you have a counterflow or a parallel flow heat exchanger. But I think it's a little bit easier to define it in terms of where the specific location is. Right? Okay, so what do I mean by that? So let me go ahead and draw our heat exchanger one more time. Okay. We have our two fluids here, fluid 1 on the inside, fluid 2 on the outside. Okay. So delta T1 would be the difference in temperature between the two fluids at this physical location, right? Now, whether this is inlet or outlet depends on if it's parallel flow or counterflow, but this definition kind of works for both. Right, so what we can say is that we can compute delta T1 here, right? So we have T1 inlet, and let's say this is a parallel flow heat exchanger. Okay. That means both the inlets are in the same place. That means delta T1 is equal to T1 at the inlet minus T2 at the inlet. Okay. But if this were a counterflow heat exchanger, we'll say that this is T2 at the outlet. And so this would change. So delta T1 would be T1 inlet minus T2 outlet. Okay. So that's why, it gets a bit confusing to say, for counterflow, use this, parallel flow, use this. I think it's easier just to have this image of the heat exchanger kind of in your head and say that delta T1 is the difference of temperature at this physical location. Okay. And then on the other side of the heat exchanger, right? This is where you would compute delta T2. Okay. So in the case of a parallel flow heat exchanger, this would be T1 outlet minus T2 outlet. Okay, so with those definitions in mind, you can plug that into this formula for delta T log mean, and then you can use that together with your thermal circuit. Okay. Okay, so this basically gives us an alternative way to compute the heat exchange. Okay. Now I know in the beginning I did say that we didn't need the temperature difference. We still kind of do. So we still need the inlet and outlet temperature difference here. But by giving us an alternative formula to do to compute this gives us another way to compute those inlet and outlet temperatures. I think it'll make more sense once we do this next example. Okay. But basically, we have two ways to compute the Q of the heat exchanger. We have the thermal circuit way, and then we have the way that we talked about on Tuesday, which involves the mass flow rates and the thermal capacities of the fluids. Okay. And you'll see those two kind of ways interact in the next example. All right, any questions before we jump into that example?
No, we can hold there first.
Oh, yeah. So this next example is pretty cool. It's we've gone over a lot of formulas, but this next example you'll see is actually pretty practical. So very reminiscent of something you'd actually solve for in a real practical heat exchanger situation. By the way, I forgot to mention this at the beginning of class today, but one other thing that I posted on Canvas was what I call kind of a convection summary handout. So I think the convection unit is pretty challenging just because there's just so many formulas that we've gone over. So that handout, I've kind of made it in a way to kind of summarize everything. What situations you use the Nusselt correlations. When what turbulent flow is, what laminar flow is, all the different non-dimensional numbers. I have a lot of figures in there. So definitely check out that summary handout, to help you with your study. Okay. It's a little bit too long to bring to the exam. It is, I think on Tuesday I said it was 6 pages. It's actually 9 pages. That just kind of shows how much that we've done. But I think it's a little easier reading through that handout versus going through all the lecture. Okay, so let's jump into our example here. Okay, so let's say that we have a counterflow heat exchanger, Okay. And we have the exchange of heat between motor oil and water. Okay. Okay, so let's draw the figure first. So we have our concentric tube heat exchanger, just because that's the only one we know how to do. Okay. We'll say water is in the inner pipe. And we'll say the motor oil is in the outer pipe. Okay. We know that this heat exchanger is in counterflow. So let's draw the fluids going in opposite directions. So we'll say the oil is going from left to right. And the water is going from right to left. Okay. Let's see. Question, yes.
Are we considering the thickness of the inner pipe or not?
We are not in this case, so we're ignoring that in this case.
Thank you.
All right, so mass flow rate of the water in this problem is going to be 0.2 kilograms per second. And then mass flow rate of the oil is 0.1 kgs per second. Okay. All right, inner diameter for this inner pipe here, we'll say is 25 millimeters. And then outer diameter for the entire annulus is 45 millimeters. Okay. Okay. We also know the inlet temperatures, so we know the water. So T water at its inlet, it's coming in at 30 degrees C. And then for the oil at the inlet, this is coming in at 100 degrees C. Okay. So in this particular case, our oil is our hot fluid and our water is our cool fluid. So the oil is going to cool down, water is going to heat up. Okay. Okay, I think that's all the given information. Yes. Okay. So in this case, we want to compute. Okay. What we want to do is we want to compute the length of heat exchanger necessary. So the total length that's needed to cool down the oil from 100 degrees C to 60 degrees C. Okay. And so this design requirement, actually also sets our outlet temperature for the oil. Okay. So that means our oil outlet temperature is going to be 60 degrees C, or we're going to design this heat exchanger so that the outlet temperature is 60 degrees C. Okay. So there's quite a lot of steps to this problem, and so we're going to have to kind of make use of everything that we've learned up until this point. But are there any questions on just the setup for the problem? Anything that's given here? Okay, good. Okay. So how in the heck are we going to get length from all these equations that we have, right? Because that's kind of the unknown here, right? So length is going to be this entire length here, okay? So we want to find out what that length is going to be. Okay. So first, just so that we can do a little bit of strategizing, let's see from the equations that we've gone over, which one is going to allow us to compute length. Okay. So for a heat exchanger, it's always good to start with the equations for the heat transfer in the heat exchanger. Right? So we have Q hex, right? So there's actually, two ways that we can compute this, right? So one way, since we know the inlet and outlet temperatures of the oil, let's start with that. So since we know the inlet and outlet temperatures, we actually know the mass flow rate as well, right? So the Q of this heat exchanger has to be m dot oil times Cp of the oil, okay, multiplied by the difference in temperature at the inlet and outlet. So T oil inlet minus T oil out. Okay. Okay. So of course, we do need the thermal capacity of the oil itself. Okay. But this is something that we can compute, right? Granted that we look up the Cp of oil. So this is the number that we can compute. Okay. All right, so that's great. But nowhere in this equation that we can compute the length from this, right? So length does not even show up in this equation, but we are going to use this equation at some point. So we can compute this, but length does not show up. Okay. So our main design variable is missing from this equation, even though we can compute this equation. Okay. Okay. And actually, we can actually use this equation to compute the outlet temperature of the water as well. So remember, that was kind of like the example we did last, right? Remember, all the heat that's lost from the oil, we're going to assume is gained by the water as well, right? So this is m dot Cp of the water multiplied by T water at the outlet minus T water at the inlet. Okay. So we can use this to compute this. Okay. Great. So now we have a way to compute, the outlet temperature of the water, but still, we don't have any length here. But at least we're making progress. At least we're kind of writing down what we know and, computing things about this system that we know about. Okay. Okay, so let's try something different. Let's come up with another equation that we have that we can use to solve for F. Okay. So how about our thermal circuit equation? So for our thermal circuit equation, we have Q hex is equal to delta T log mean divided by the sum of the resistances. Now, we're assuming that there's no conduction resistance through the wall. So we only have two resistances here. So we have 1 divided by H of the water times the surface area of that inner pipe plus 1 divided by H oil times the surface area of the inner pipe. Okay. Where this A in this case is going to be the same for both fluids, because that's the interface in which they're interacting. Okay. So this is the surface area. Okay. Right, so the surface area of the inner pipe is pi times the inner diameter times the length. Okay. And so if we plug that in fact, if we factor it out, so Q hex is equal to delta T log mean divided by 1 divided by pi di times L multiplied by 1 over H water plus 1 over H oil. Okay. And so if we look at this equation, we actually have an expression here that has the length of our heat exchanger. Right? So that means we're going to have to involve this equation in some way in order to compute the length, because that's the only way it's going to show up is if, you know, if we have this this formula here. Okay. All right. So now based on all these equations here, you know, hopefully you'll kind of see kind of the approach that we need to take. So first thing we're going to do, right? First thing we're going to do is we're going to compute the heat transfer in the oil based on its inlet and outlet temperatures. Okay. And then based on that, we're going to use that to compute our outlet temperature of the water. Okay. Then we're going to use that same heat transfer in this equation here. Okay. And use that heat transfer to compute L from here. Okay. So this problem is, you know, like I said, you know, quite complex. There's quite a few steps to it. So, you know, I want to take a minute to kind of, you know, strategize, you know, how we're going to do this, because yeah, when you have a problem like this, it's difficult sometimes to know kind of where to start. And so, you know, I want to kind of walk through at least kind of my thought process in terms of, you know, how we would start something like this. Okay? So I think sometimes, you know, when you look at example problems, especially in the textbook, they kind of magically know what to do for the first step. But when you're coming to a problem for the first time, you know, coming up with that first step in a lot of ways, I think is the hardest part of the problem itself. So, you know, a lot of times, you know, when you're coming to problems like this, I always just like to write down, you know, what are some of the relevant equations? What are things that we can compute based on what we're given? And then from that, and as you write down more equations, you know, the path forward in terms of how you actually solve the problem becomes a bit more clear. Which, you know, again, I did this in about 5 minutes here. You know, this probably goes a lot smoother than, you know, if you were to try to solve it for yourself too. So, you know, when you're looking at these problems, you know, definitely take some time, strategize, think about how you would approach it. And, you know, sometimes it takes, you know, 10, 20, 30 minutes to kind of come up with a good approach. And, you know, that's okay. So don't feel bad if you know, don't know kind of the path forward, because, you know, I think examples and things like that make it seem easier than it actually is. Question?
What was that whole denominator mean? C.
Oh no, it's an L. So this is the surface area of the pipe. So it's 1 over pi times di times L.
Oh.
Yeah. Mhm.
Oh, okay.
Yeah.
Okay.
Mhm.
Thank you. That's only because you're assuming that there's no induction resistance.
Exactly.
It's only two diameters.
Exactly. Yeah. Yeah. So if we did have the conduction resistance, it would make this expression a bit more complicated. But yeah, for this case, we're assuming that there's okay, so we have a lot of things to compute in this problem. So let's start with the obvious. So let's start with this equation up here, since we have everything that we need. Okay. But actually, you know, we don't have everything we need. We need the fluid property. So let's start with that. Okay, so we have two fluids here that we need to compute properties for. Okay, so let's start with the oil. And this is actually relevant for the homework as well, because the homework also uses motor oil. So for motor oil, the table in the textbook that has oil properties, and this is one you'll have to use the table for because the online calculator does not have this. So motor oil is table A5 in the book, so that's in the appendix of the textbook. Okay. And so if we assume a film temperature of 80 degrees C, because we know that the oil is going to go from 100 degrees C down to 60, 80 is kind of right in the middle of that. Right? We get the following properties. So we have Cp is equal to 2131 joules per kilogram Kelvin. We have the dynamic viscosity equal to 3.25 times 10 to the minus 2 Newton second per meter square. And we have its thermal conductivity of the fluids equal to 0.138 watts per meter Kelvin. Okay. Okay, and then we have for water. Okay. Now for water, this is going to be a little bit trickier just because we don't have the outlet temperature of the water just yet. We are going to have to make an assumption here. Right, so we don't know the exact outlet temperature, but we do know the water is going to heat up. And so if we assume a film temperature that's higher than what we started at, that's usually a pretty good assumption. Okay, so we know the water starts at a temperature of 30 degrees C, and it's only going to go up from there. And so if we assume a film temperature of 35, okay, that should at least get us in the right ballpark, right? Okay, so at 35 degrees C, the properties of water, we have Cp, thermal capacity is equal to 4178 joules per kilogram Kelvin. Okay. Dynamic viscosity is equal to 725 times 10 to the minus 6 Newton second per meter square. And we have the thermal conductivity of water is equal to 0.625 watts per meter Kelvin. Okay. Question, yes.
A lot of the times, like say, for example, even in the homework, rather than me having us compute the film temperature,
Mhm.
you just give it to us.
Yeah.
Does it sometimes get complicated to?
It does. Yeah, so if you really want to do this problem, since we don't know the outlet temperature of the water, we're making this assumption of 35. I think for the oil, I think 80 is pretty reasonable because we know it's going between 100 and 60. But if you really want to do this problem more accurately, you would compute the outlet temperature of the water. If that outlet temperature is much higher than you originally thought, you would have to recompute this entire thing and recompute the properties of water. So yeah, it's a little bit of iteration if you really wanted to be accurate with these calculations.
Oh, thank you.
Okay. So now that we have the CP of the oil, right? This was kind of the main one that we were looking for, at least from the beginning, okay? And so we can use this CP of the oil, bring it all the way up here, and use that to compute Q hex, okay? Okay, so we have Q hex is equal to m dot of the oil, CP of the oil, multiplied by its inlet and outlet temperatures. Okay. So we have everything for that. And so we get a amount of heat transfer of 8,524 watts. Okay. All right. And then based on this quantity here, we can use this to compute the outlet temperature of the water. So we know that the same Q hex is equal to m dot CP of the water multiplied by its difference in temperature. Okay. So that's going to be the same thing as that. Okay. So it's a little bit of algebra here. So you have to divide by m dot CP of the water. You would add in the inlet temperature of the water. And what you get from this is E water at its outlet is equal to 40.2 degrees C. Okay. So in this case, our selection for the film temperature of the water was a good one. So the water we know heats up from 30 degrees C to 40 degrees C. So 35 is right in the middle. So, it's like I did this problem before. So I know exactly what film temperature to do. Okay, good. So now that we have Q hex, now that we have the outlet temperature of the water, we can now plug these guys into our thermal circuit equation. Let me go back, switch from red, okay? Because we know that Q hex is equal to delta T log mean divided by, actually, let me bring that that surface area up top. So we have times di times pi times the length divided by 1 over h of the water plus 1 over h of the oil. Okay. Okay. All right, so for this equation here, we can solve this equation for L, right? So L is equal to Q hex divided by delta T log mean, okay, multiplied by 1 over HW plus 1 over H oil, okay, divided by DI times pi. So times 1 over DI times pi. Okay. So we have a lot of the quantities here. So we have Q hex. So we did that in the last step, right? Delta T log mean, we can compute that because we know the inlet and outlet temperatures of all the fluids, okay? DI, we know from the problem. Pi is just pi, we know that, okay? The last thing we need to do to finish this problem is to compute the convection coefficients for the water and the oil, okay? Yeah, so quite a long problem. So now, after all of that work, now we have to compute Nusselt numbers and compute H's. And so, yeah, this was a long problem, right? I think it's a good one, right? It kind of showcases kind of everything that we've learned up to this point. Okay. All right, so let's start on this. And so let's run through our convection problem-solving methodology to solve for these two convection coefficients. And we'll just do them simultaneously. There's no need to go through the process twice. So we'll just do kind of the same steps, but for both fluids at the same time. Okay. So step one of the convection problem-solving method, remember, is to identify the flow type as well as identify the flow geometry. Okay. So we're going to do this twice. So one for the water and one for the oil. Okay. So for the water, we have flow in a pipe. Right. So that's our internal flow. And then for the oil, we have flow in an annulus. Okay. Right. Both of these are internal flows. But that means, the equations that we're going to use for our Nusselt number are going to be different between those two situations. Okay, number two. Number two is to compute the fluid properties. Right. We need the fluid properties to compute the Reynolds number and the Nusselt number, all that good stuff, right? Luckily for us, we've already done this for this problem. All right, so we've already looked up the data tables. We have the fluid properties for both the water and the oil. So that one is good and done. Okay. Okay. Step three is to compute the Reynolds number. And the main reason we do this is to determine whether the flow is laminar or turbulent. Okay, so for this one, we do need to do some calculations for this, okay? Let's start with the water. Okay, so the Reynolds number, and remember, since we are in internal flow, we're gonna do the Reynolds number based on the diameter of the pipe. Okay. That's equal to density of the water multiplied by its mean velocity, multiplied by the inner diameter, divided by its dynamic viscosity. So we're not explicitly given the mean velocity here, but we can compute this based on the mass flow rate. Because remember, mass flow rate is nothing more than just the mean velocity multiplied by the cross-sectional area multiplied by the density. Okay, so we have UM of the water is equal to m dot water divided by density. Lost my place. Multiplied by the cross-sectional area, which is pi over 4 di squared. Okay. We plug all that in, plug in the density, the fluid properties, mean velocity, inner diameter. For the water, what we get is a Reynolds number of 14,050. Okay. Which, is very turbulent. So since this is above 2,300, this is turbulent. Okay. For the oil, so for the oil, once again, we're going to be computing the Reynolds number, but remember, oil is flowing in the annulus. And so that means, wherever we see diameter, we're going to plug it in with hydraulic diameter. Okay, so for this one, we have density multiplied by the mean velocity of the oil. Okay. We have hydraulic diameter for that, divided by the dynamic viscosity of the oil itself. Okay. Now, once again, we're not given the mean velocity, but we can compute it in the exact same way. So let's compute this from m dot oil. Okay. So basically, our mean velocity in the oil is going to be m dot oil divided by the density of the oil multiplied by pi over 4. Okay. Now for this one, we're computing the cross-sectional area of that oil part. And so this is going to be dO squared minus DI squared. Now DH here is simply dO minus DI. Okay. All right, so we plug all these values in. It's a lot to plug in, so a lot of values. So definitely take your time with these things. But we plug all those in, we get a Reynolds number of 56.0. Okay, which, since this is less than 2,300, is going to be laminar flow. All right, any questions on this so far? Okay, good. So now that we have the Reynolds number for both flows, and you can see one of our flows here is turbulent, the other is laminar. We have all the information we need to compute the Nusselt numbers. So let's go to step 4. Let's go ahead and compute the Nusselt number. So let's start with water first. right? So for water, based on the Reynolds number that we computed, this is turbulent flow in a pipe. Okay. And so for turbulent flow in a pipe, we have the following Nusselt correlations. We have Nusselt number based on the diameter is equal to 0.023. Reynolds number based on the diameter raised to the 4/5 power multiplied by Prandtl number to the n. Okay. Well, remember, n is a special parameter. It can either be 0.3 or 0.4. Okay. That's you. Okay. And so that value of n there is equal to 0.3 if the fluid that we're considering is being cooled. Okay. Or it's equal to 0.4 if the fluid that we're considering is being heated. Okay. Okay. So this is for the water. And so we know the water is raising in temperature, right? So the water is being heated from 30 degrees C to 40 degrees C. That means the value of n that we're going to use is 0.4. Okay. Okay, so we plug everything in and we get a Nusselt number of 90 for the water. Okay. Okay. Then we have the oil. Right? So the oil, we have laminar. The type of flow that we have here is laminar flow. We have laminar flow in an annulus. So for laminar flow in an annulus, this depends on the ratio of DI over DO, right? Remember, this is the table that we went over kind of at the beginning of class today. So our ratio of DI over DO, we take that ratio, which is 25 over 45. It's about 0.56. Okay. And so from the table that we found earlier today, we get the Nusselt number. It doesn't quite fit into the table. So I think the table has an entry for 0.5 and 1.0. So if you want it to be more exact, you could interpolate in the table. But we'll just say this is close enough to 0.5. And so our Nusselt number in this case is 5.74. All right, so now that we know our Nusselt numbers, our last step is to compute our convection coefficients. Okay. All right, and so our convection coefficients for both cases is going to be the Nusselt number multiplied by the respective thermal conductivity divided by the respective diameter. Okay. Right, and so just since we're just about out of time, I'm just going to write these numbers down. So for our convection coefficient for the water, we get a convection coefficient of 2250 watts per meter squared Kelvin. And for the oil, we get a convection coefficient of 39.6 watts per meter squared Kelvin. Okay. All right. Yeah.
In the diameter, the
Hydraulic diameter. Yes. Yeah. Yeah. So make sure whenever you have an annulus flow, you make sure you use the hydraulic diameter. So now that you have all this, we have everything we need. And so if we come back up here, we can compute everything here for L. Okay. So we are out of time. So I'm just going to say that, plug everything in. Plug all that shit in. And what we get is L is equal to 65.9 meters. So really long ass heat exchanger. Like we said, you can coil the heat exchanger around to get this length. So.
Like that.
All right, any final questions before we head out for today? Okay, so actually one quick thing. So I didn't get quite to finish everything. So there is one last thing on heat exchangers, but we are just gonna skip it. So when you're doing the homework. Real quick, sorry guys, I know we're going over time. So for problem 2 on the homework, if you look at parts, problem 2, part H, I, J, and K. You don't have to do those ones because we didn't get to it. So problem 2, just do parts A, B, C, D, E, F. Just go up to F actually. So just go up to F on problem 2. Okay. So everything G and below, you don't have to worry about it for this problem. Okay. All right. Thanks everyone. I apologize for going over time. Have a great weekend. I'll see you guys next week.
Can you go back to the next one?
Yes. Yeah. Yeah. Photo oil. Yeah. That's probably fine. You'll probably get pretty close. Yeah.
I think it's, we're saying, say for example, we have low geometry on the surface.
Yeah.
It's a mixed boundary there. And we're doing so, I don't know, like say for example, this problem, number 2.
Yeah.
You asked, what, like how, when does it become turbulent?
Yeah.
The total length is 7.5, but it becomes turbulent at 0. Consider that, actually ended up using mixed boundary layer rather than making turbulent, because even though that's like what really I would think.
I would say it's a way to recognize it.
Okay, let me try to.
Okay. Because that's surface area usually. Or even for the annulus, right?
Oh, I see.
Right, so you wouldn't use the outer diameter because the heat's not leaving the outside. So in this case, they both have the same surface area because that's where the exchange thing is. It's just one's on the oil side, one's on the. The hydraulic one is just kind of a special diameter. We use this for the Reynolds number. But for anything geometric, we just do the. Yeah.
Question because question 3, you asked us to find the
Yeah.
and we ended up getting a value of 5,100.
Yeah.
But the thing that I'm confused about is that you give us the value of the radius. It says that the radius is going to be 0.12, but then when I plug in 0.12, it doesn't. Because you're supposed to plug in the diameter.
Yeah.
Not the radius.
Oh, okay. So you're getting twice that if you plug in the value.
Correct.
Okay, that might have been typing it up. Probably should have plugged in. That's probably what you should have.
Yeah, because I always try to like, wait, let me make sure that I'm incorrect.
Yeah,
You know, if anything, you're the professional.
yeah.
So I try to look, I feel like that might be.
Yeah. I think that is, I probably plugged in the rate. But yeah, thanks for, I'll double check next week.
Oh, and also,
Mhm.
how do you know